Well, hello and welcome again to Math 315. This is the third recording in Chapter 9. And as I mentioned, this is quite a hard chapter. You may need to watch some of these videos a few times to try and get at least some of the ideas sorted out in your mind. You'll see from the tutorial problems what sorts of questions one might be asked about this fairly complicated material. So we've been looking then at, we finished off last time looking at the axioms of the real numbers, and we saw we had a number of so-called field axioms, then the axioms of order to give an ordered field, and then the final, the axiom that separates off the real numbers from the rational numbers was the fact that any non-empty set which is bounded above has a least upper bound or supremum inside the set that you're working in, and that distinguishes the rationals from the reals. Now I want to mention briefly this Archimedean property, which we're going to use in a moment as well, and among the many properties, this is a theorem that you can derive from the axioms that we had listed before. I won't give a proof of that, but among the such properties you can derive is a so-called Archimedean property. It goes back to Archimedes, the ancient Greek, who first, probably didn't have a particularly deep understanding necessarily, one doesn't know, but he certainly had the following idea. So if you take x to be any real number and y is any other real number, so again I like to draw little pictures here, so we're thinking here of y is up here, and so this might be 0 here, and here's x might be very small, and y might be very big. So think of x as being very tiny and y is very big. Then what it says is that you can always take this number x, no matter how small this is, you can multiply it by a big enough integer, big enough positive integer, and make it bigger than y. Seems sort of obvious, but it's actually a very subtle idea. So you take any real number x, think of it as being very small, think of y as very big, then all this says is you can multiply this x by a big enough positive integer to beat y, to get on the other side of y. This principle, in fact, is what's used by people in the modern world to make lots and lots of money. For example, if I asked you for 1 cent, we don't have 1 cent coins anymore, but if I asked you for 1 cent, you'd say, oh, well, here you go, take a cent. It's not worth much. On the other hand, if you asked every person in Australia to give you 1 cent, then you've got a lot of money. And that's exactly what many banks and other institutions do. They take a small amount, and you say, oh, well, it doesn't matter very much, but they take it from a large number of people, and suddenly it's worth a lot of money. That's the Archimedean property. So again, here I said, here we think of x as being very small, y is very large. And I've just done a little example here. So if x is 0.00001, so it's really small, and y is 1,000, can I make this bigger than 1,000? Yes, I just multiply this number by, say, 10 to the 8. Well, perhaps I'll make it, so 10 to the 8 would move 1, 2, 3, 4, 5, 6, 7, 8. We probably need this to be, say, 10 to the 9th, perhaps. Make this 10 to the 9th, and then definitely this is bigger than this one. 10 to the 8th, they're equal to each other. So if I take, say, 10 to the 8th, then a 10 to the 9th, if I multiply this number by 10, a 1 with 9 zeros on the end, then I'll get bigger than this one. And that's the Archimedean property. Now, in terms of real numbers, it essentially says there are no such things as what people call infinitesimals in the real numbers. If you hear people mumbling about infinitesimals, then you can tell them that they know what they're talking about. You can actually define infinitesimals But that's a whole new area, and that's quite different to the real numbers. But in the real numbers themselves, there are no infinitely small quantities. There are no infinitesimals. Originally, calculus was done in terms of these objects which don't exist, called infinitesimals. And some very old books still mumble about these, but they actually don't exist. There are no infinitely small real numbers because of the Archimedean property. Now, one of the theorems we've been using quite a lot was the monotone convergence theorem, the MCT, and we didn't actually ever prove that. And the reason we didn't prove it is that we actually need the idea of least upper bound. And so I didn't give a proof then, but for those interested in seeing how the monotone convergence theorem is proven, then I'm going to do it here. If you're not interested in that, you can skip to the next little section. So here's a proof of the monotone convergence theorem. So suppose we've got AN as a monotonic increasing sequence which is bounded above. Now remember, the monotone convergence theorem says that then in that case, if there's a brick wall and it's monotonic increasing, this has a limit. So I've got to get some sets into it, so I'm going to put S to be equal to the set of all these sequences, set of all these numbers. So again, think of it, I like to think graphically all the time. So here we have, there's A0, A1, A2, so the terms are getting bigger. There's a brick wall somewhere, it's bounded above. Now, by the least upper bound axiom for the real numbers, this set S it's bounded above, so it's got a least upper bound. I'm going to call S, it's got a supremum. So there's my set S, consists of these points here, and there's the supremum S, it's the least upper bound for this set. Now we claim that the limit of the sequence as n goes to infinity is this supremum, it is S. And the proof's a little bit technical, but it goes like this. Given any epsilon bigger than naught, so think of epsilon as being 0.1 or something, a small number, then if I go back a little bit, so I'm going to take S minus epsilon, so there it is, that is not an upper bound for S, because it belongs, well, it's not less than every element of the set. It's not a least upper bound because little s was the least upper bound, and it's not an upper bound either because it's less than the least upper bound. So that means there is an integer capital N, so that you can take a term in the sequence a sub n, there it is here, and that will be on this side, that is, it's bigger than s minus epsilon. It's bigger than s minus epsilon. Now, since the sequence is increasing, then if I go past that term, if I go little n bigger than capital N, then this term is less than the a sub small n. So if I go past that point, a sub n is less than a sub little n. Now that means then, because this was bigger than that, therefore this is bigger than that. So a sub n is bigger than s minus epsilon. And I can rearrange this equation and write this as s minus an is less than epsilon. And I can take absolute values of both sides, nothing goes wrong because everything's positive. So the absolute value of s minus an is less than epsilon. And of course with absolute value I can turn the terms around and write this as a sub n minus s. That will be less than epsilon if n is bigger than capital N. But of course that is just our definition of what we mean by the limit. The limit was that if an goes to s, then there exists a capital N, so that if you go past that point, the difference between the sequence and its limit is less than epsilon. So this is the definition of the limit. So that's why we didn't do the proof earlier. We needed this idea, it's quite fiddly, and we also needed this idea of the least upper bound axiom. Okay, well, our next little bit is just to look at some statements about real and rational numbers, and also to look at some irrationality proofs. So here are some basic facts about rational and irrational numbers. Firstly, between any two rational numbers is a rational number. That one you can do in the tutorials. You might think about that. If I give you two fractions, can you find a fraction between them? Between any two fractions, any two rational numbers, there is an irrational number. Now that's a little bit harder, and I'm going to lead you through that in the tutorial problems. That is, I give you two fractions, can I find an irrational number between them? That's a bit harder. See the tutorial problems for that one. Between any two rational numbers, there is an irrational number. Well, that one you can probably do once you've got these two established. And finally, between any two irrational numbers, there is a rational number. Now that is the hardest of these. I give you two irrational numbers, you've got to find a fraction between them. And that's the one I'm going to give a little proof of here. Between any two irrational numbers, we can find a fraction. So suppose we have two irrational numbers, a and b, where a is less than b. So here again, look at the picture here. I like little pictures. There's a, there's b. Just think of that for the moment. Now I'm going to construct a rational number in a minute that's between the two of these. I'm going to cook up a rational number between a and b. Now these might be very, very close together. Okay, these might be extremely close together, these two irrational numbers. In any case, I'm going to measure the distance between them. So d is this distance, b minus a. So that distance there is d. Think of d as being very, very, very tiny. Think of these two numbers as being very close together. So d is very tiny. Well, no matter how tiny it is, I can hit it with the Archimedean property that, even though this might be very small, I can take a magnifying glass and I can blow this up. I can multiply by an integer n that makes this distance here bigger than the number 2. So this distance might be, for example, 0.1. So I can multiply it by, say, 300. And that'll be bigger than 2. That's the Archimedean property. Now essentially what you do now is you take a magnifying glass and you kind of magnify this up by a factor of n, this integer. So you magnify this up by a factor of n. That is, I multiplied this by n, that becomes na. Multiply this by n becomes nb. So I'm now looking at this little section here. So I magnify this up. Now I ask, well, what's the difference between these two? Well, the distance between nb and na is, factoring out the n, is nb minus a. Now b minus a was my d, and nd was bigger than 2. In other words, this distance here is at least 2 units long. Now if I give you an interval that's at least 2 units long, then there must be a whole number, an integer, between the two. So there was a gap of at least 2 between an and ab. Sorry, that should be nb. So there's at least a gap of at least 2 between an and nb. And that means there's at least one integer, one whole number between the two, because the gap's of 2 units long. So I'm going to call that number m between the two. So there's an m, which is a whole number in between the two. And now the trick is you take away the magnifying glass and you go back to here again. So you now divide all the terms in here by n. This goes, you're really taking away the magnifying glass. This goes back to a, this goes back to b. You're dividing by n. This is m over n. And of course, m over n is a quotient of two integers. M and n were both whole numbers. And so we found a rational number, m over n, between the two given irrational numbers. It's a complicated proof. It's a very lovely little proof using the Archimedean property that between any two fractions there is a rational number. Now, little example here. The ancients used to often approximate pi by root 10. It's not a bad approximation. I mean, generally you use things like 22 on 7 and so on. But you can actually approximate pi by root 10. They're not too far away from each other. And I'm going to just illustrate this proof up here. I'm going to find a rational number between pi and root 10 using the same ideas we had up here. So I'm going to illustrate the proof above to find a rational number between the two. So from the calculator, I work out root 10 minus pi. That's my d, and I get roughly 0.020685. And I want to multiply this by something to make it bigger than 2. So if I multiply it by 100, then that'll make this bigger than 2. Now what we did above was we then took a magnifying glass to these two numbers. So I multiply 100 times pi. So I'm using the 100 from here. 100 pi is 3.14159, and 100 root 10 is 316.227. And you can see there is a whole number between them, between 314 point something and 316 point something. 315 lies between them. And so finally then I now go back and take the magnifying glass away. I divide by 100. And so the fraction 315 and 100, which of course we'll simplify down, lies between pi and root 10. And there is a rational number between the two. We'll do a little bit more on that in the tutorial problems. Finally, for this bit, I want to do a little proof of irrationality. We're going to prove that log of 7 to the base 2 is an irrational number. Now, this is an important sort of problem. This is now in the high school syllabus. It's in the extension 2 syllabus, so it's an important example here to make sure you master, and there's more in the tutorial problems. So I'll just go through the proof of this. It's not that difficult, in fact, and good revision of our logarithm properties. So suppose that log of 7 to the... We're going to do this by contradiction. So I'm going to suppose that this number is in fact rational. And I'm going to show that that leads to a contradiction, that turns out to be impossible. Okay, so supposing it's rational, that means I can write log of 7 to the base 2. Remember what this means. It says, what number do I raise 2 to get 7? That's what we mean by a logarithm. So let's suppose that the value of this is p over q. Let's suppose it's rational, where p and q are integers. P and q are integers. Now what I want to do firstly is I want to get rid of this logarithm. So I've got to remember what this means. This says I have to raise 2 to the power p over q to get 7. That is, 7 is equal to 2 to the power p over q. That's what we mean by logarithms. Well, it's still a bit complicated because I've got to take the qth root of 2. What on earth's that? Well, that's too complicated. The qth root of 2 raised to the power p. So I'm going to raise both sides to the power q. I'm going to raise both sides to the power q. So 7 to the q, 2 to the p over q to the power q just gives me 2 to the p. So I'll just write down here what I did. We raise both sides to the power q. Now we get that. Well, hang on now, I look at this and I'm a bit nervous because this is 2 multiplied, the p and q are whole numbers. In fact, I should have put up here perhaps positive integers. These are positive whole numbers. So this says you multiply 2 by itself p times. Well, whatever you get, it's going to be an even number. On the other hand, if you multiply 7, you keep multiplying 7 by itself, you always get an odd number. So now I'm in the crazy situation where I've got a number which is even, but it's also odd. Well, there's no such thing. So this is impossible. This is a contradiction, and therefore log of 7 to the base 2 is in fact not a rational number. And that will be the end for this recording.